Hello everyone, it's my pleasure to introduce Dr. Lingxi Xie. He is a senior researcher at Huawei Inc. His research interests include computer vision, multimedia information retrieval, and machine learning. He has a lot of research work on generic image classification, image retrieval, and other vision problems. Recently, he has been working on deep learning, especially the model based on convolutional neural network. Before he joined the Huawei, he obtained his bachelor and PhD degrees from Tsinghua University. Now today, he will be presenting on Pangu-Weather, accurate media range global weather forecasting with 3D deep neural network. Welcome, Dr. Xie.
Okay, thank you. Okay, thank you for the introduction. So my name is Lingxi Xie, and I will introduce Pangu-Weather, an accurate medium-range global weather forecasting system, and we developed the system using 3D deep neural networks. In particular, it's a kind of deep learning model. Specifically, it's 3D transformers. So I will introduce our work following this outline. First, I will introduce the background of our work. So why we are using AI to solve the NWP, the numerical weather prediction problem. And then I will introduce the main part of our method, the Pangu-Weather, using 3D deep networks for accurate weather forecasting. And then I will show you some typical results of our algorithm. And finally, I will share you with some future perspectives we have. Okay, so let's start with the first part, the background. So the task description of the NWP, or numerical weather prediction, is like here. We are given a set of weather variables at the current time, and we hope to predict the weather variables in the future, for example, 3 or 5 days later. So it is a daily, it's very related to our daily activities for everyone. So every day when we go out, we want to track the weather forecasting to see whether it will be raining today. So you will know that everything that was reported by the like the weather agencies are generated or produced by some kind of numerical weather prediction algorithms. And previously, these algorithms were not developed by AI or by the deep learning, and now we are using deep learning to develop a stronger algorithm for this part. So we know that mathematically the task is to learn a function f. That f receives the current weather data or weather variables as input and produces the weather data in the future as the output. So this formalized definition is very important because when we know the input and output of our system, we can use something like deep learning to develop the function f. And what we need is to learn the parameters using deep learning to determine the function f we need. Okay? So there are two main lines of research for NWP. The modern NWP, the numerical weather prediction, starts in the previous century, like in 1904. But in a very long period of time, it was developed by using some physical equations or partial differential equations to describe the transition between the weather states. But recently, starting from something like 2016 or 2017, people started developing AI-based methods to estimate the function f using deep neural networks. So it is a direct, it's a consequence of the fast development of deep learning, because deep learning is a very powerful toolkit that you can use it to learn very complicated equations or functions, even though you do not know why it works and what is inside the function. But deep learning can learn that if you have sufficient training data. Okay, so this is an example. If you are familiar with NWP, then it's very natural. But if not, you can see that this is the current state of our weather data, and you want to predict what it will be in the future. For example, this is a 2-meter temperature, this is a 10-meter wind speed. So it is the revolution of these things in the future. Okay, so going into AI, so we know that you may be quite familiar with AI, but I want to just say one thing, that AI is working on replicating human intelligence with mathematical methods. So this is very important. The core of AI is mathematical methods. The key problem is to find the relationship between input data and output data. So if you have a determined form of input and output, then you can build up an AI system and use some tools like deep learning to develop the function. And recently, deep learning emerges like in 2011 or 2012. It's a very powerful toolkit that you can use it to learn very complex functions with hierarchical definition of the network. So it's a layered design of a mathematical function that it contains millions or even billions of parameters, and you can use your training data to tune the parameters. And after a sufficiently long training procedure, the parameters converge to a relatively steady state, so that they can build up the relationship between the input and the output. Okay, so it's deep learning. And also, as the fast development of deep learning, people started considering using this method for science. What does it mean for science? That is to solve some problems that was not solved by AI in the past. This field is called AI for science. Once again, it is using AI algorithm to solve some problems which were not solved by AI in the past. For example, the first thing we can see is to use AI to solve some gaming problems like playing chess or video games. A very famous example is AlphaGo and also AlphaStar to play the game of StarCraft, and also AlphaFold to solve the problem in life and the biology. And also we can see something to solve the geophysics problem and to develop a efficient system for nuclear fusion using AI. And in the second page, we can see that using AI to solve some mathematics problem. Here, I did not include some recent developments, like Google developed an algorithm named Alpha Geometry that can solve some geometry problems, and also computing theory that using the AI to develop a faster quicksort algorithms or something like that. And finally, we can see something like weather forecasting, whether nowcasting or weather forecasting, which differ from each other in the lead time, in the length of lead time. Okay, so this is what we have, and today we are focusing on this part, the medium range weather forecasting, which means that we want to use the current weather data to predict the future data in about 3, 5, 7 days or even longer. So this is the weather forecasting problem. So this leads to a very direct question, that why these problems which were not solved by AI can be solved using AI at the current point, or why we are using AI for NWP in this research. What is our motivation? So we think there are two major principles that you can use to determine whether a problem can be solved by AI, or AI can solve the problem better than the conventional algorithms. The two principles are, first, the human experience is insufficient to formulate the complex system. And the second one is data is sufficient for training models with a large number of parameters. So in the numerical weather prediction problem, we can see that the manually designed PDEs, that is the conventional algorithm, it involves approximation or parameterization, and both of them are quite complex, and we can see that the error can accumulate across the entire forecast time. And as you are increasing the lead time longer and longer, the errors can accumulate very fast. And in the past decades, we can see that meteorologists tried to develop more and more sophisticated systems to add more equations to complement the system, but the speed of evolution is slower and slower. In the past 10 years, we can see a clear slowing down in the development in the accuracy of the NWP system. So this one shows that the human experience may be insufficient to formulate the very complex system, and may be insufficient to continuously developing the system better in the future. And in the second part, we can see that data is sufficient because fortunately, we have a very large scale data set like the ERA5 data set. It's a large scale data set offered by the European Center of Weather Forecasting, and it offers us a global weather data from 1940s to now. So it's a good test bed and a good training set for our algorithm. Okay, so if you have a problem, not limited to something like NWP, if you have a problem and you want to decide whether AI is good to solve this problem, maybe you can consider these two principles. The better these two principles are satisfied, the more likely that the algorithm, the problem you have will be better solved by AI. And a side advantage of AI in NWP is that it runs very fast. The AI algorithms are more than 10,000 times faster than the simulation-based or physics-based method. So it offers us an opportunity to run our algorithm even in a laptop without a GPU. After it was trained, although the training takes a lot of resource, but after you trained your model, you can run the model on your own laptop only with CPU very fast, so that everyone in the world, if you have the reanalysis data, you can run it on your own computer. Okay. And we have some previous work. Previously, conventionally, the weather forecasting system was established by using something like partial differential equations. So I am not I mean, my expertise is purely in AI. I did not have expertise in meteorology, so I cannot understand what these equations mean. But we can see that they are very complex, right? Right. Yes. And this is also a very small part of the paper. Throughout the paper, there are more than 100 such equations, so it's a very complex system. Okay, so previously, meteorologists are using such systems to predict the future weather. And then, starting from the 2016 or 17, we saw some algorithms to use AI. And starting from 2022, we saw that some AI algorithms can develop high-resolution global weather forecasting. What do we mean by high resolution? It means that the resolution is the same as the resolution of the ERA5 dataset. The spatial resolution is like 140. It's like 1440 times 721 in the Earth's surface. So the grid resolution is 0.25 degrees. So it's not a very small distance because around the Earth's surface is something like 26 kilometers to 27 kilometers for each grid, but the resolution is much higher than what we have previously. Okay, and also a concurrent work is GraphCast developed by Google, and they are using a graph neural network to do this. Okay, so let's go into our own work called Pangu-Weather. So before we enter the details, we can see that the weather forecasting system can be roughly partitioned into three parts: the assimilation, NWP, and the post-processing. And we are only focusing on the middle part, that is NWP, because we only have such data. For assimilation, maybe you need some data from the satellites, from the observation sites in the ground, or something like that. And for post-processing, you are using the output of the NWP to predict like what the weather will be like in Beijing, the temperature, the precipitation, or something like that. And we're only focusing on the middle part. I think the middle part maybe it's the most direct part because the input and the output form is very determined. It's a grid-wise data, so that we can do it in using deep learning. I mean, I did not mean that we can do that very easily, but we can define the form very easily. But it requires some technical efforts to train the system. Okay. So the data set and setting, we have the 5th generation of the ECMWF reanalysis data, that is ERA5 data. It offers hourly reanalysis data from the 1940 onwards. So we are using such data for training, the 39 years of weather data for training, the 2019 data for validation, and these 3 years of data for testing. This is to be fairly compared to WeatherBench, established benchmark of weather prediction. And we are using part of the weather variables, like 4 surface variables and 5 upper air variables. For the 5 upper air variables, we are using 13 pressure levels. So to be brief, the 4 surface variables are temperature, the 2 components of wind speed, and the mean sea level pressure. So this is very important because we can use this variable to predict the tropical cyclones. And the 5 upper air variables is the geopotential, specific humidity, temperature, and the 2 components of the wind speed. And the 13 pressure levels starting from the 1,000 hectopascals, that is very close to the ground, like only 100 or 200 meters above the ground, and to 50 hectopascals. This is very high, like 20 kilometers above the ground. So these are the 13 pressure levels. So the ERA5 dataset contains far more data than these. It has a total of 37 pressure levels, and we are only using about 1/3 of them. And it contains more than 10 variables in both the surface and the upper airs, and we are only using a small part of them. The full data set is over 2,000 terabytes, and we are using about 60 terabytes of data. It's quite a large data set, right? Okay, so it offers us a sufficient training data to train this model. And the input and the output of the deep neural network is very determined. It has more than 70 million variables because in an Earth surface, the Earth's surface is partitioned into some grids. And I mentioned earlier, so the grid is like 1440 times 721. And you have 4 surface variables and 5 upper air variables in each of the 13 pressure levels. So you can compute this one. It's more than 70 millions. Okay, so the input is so many variables, and the output is exactly these variables in a future time. Okay, so it's the same form, but it appears in the future. So we call this prediction algorithm, the prediction task, as autoregressive. It means that to use the same data to predict itself in the future is autoregressive. It's a quite popular concept in machine learning because you know that currently the large language models are also using the autoregressive prediction to train the model. So it's a very similar framework that we are also using the autoregressive form because we have such data. We are using the past data to predict to the future. Okay, and yeah, the difficulty mainly lies in the high dimensionality of such data because you have so many variables. But for machine learning, in particular, for the modern architecture of neural networks, it's not a very big deal because we can use something like the vision networks because this data is is very similar to what we to the data we have in computer vision. So we can use the well-developed architectures in computer vision to process this data. In particular, we are using a variant of the vision transformer named the swing transformer to process such data. We are using swing because we want to accelerate the computation and to decrease the number of parameters we have. Okay, so if you are not familiar with such a architecture, don't worry because this is quite a quite popular and quite a standard model in AI or in computer vision. So every student in AI can implement such a architecture very easily, and you have a lot of open source code to use. So this is just a network architecture, and the main contribution of this work is to show that such a methodology can work. But if you are using this model, it's okay. If you are using another network model, it's also good, as long as you have such data and you can tune your model to fit such data. So the insight that AI can solve this problem very well is more important than the exact model you are using to solve it. Okay, so this is the model we have, and we have some small insights, like we are using 3D deep learning, the 3D neural network. We know that the Earth's surface is 2D, and another dimension is what we use to formulate the height or the pressure level. Previously, the NVIDIA and Google models are using 2D neural networks, but we are using 3D because we realized that the neighboring or the closing pressure levels are related to each other, right? So we are using 3D networks to better formulate the relationship between them. We think that this is very effective. And also we are using the Earth-specific prior. Maybe I will not go into this part very in details because it's a technical detail. We are assigning each neuron in the network with an absolute coordinate so that it can realize what the neuron is corresponding to, where the neuron is corresponding to, so that it can predict its variables more accurately and more easily. If you are interested in this part, maybe you can refer to our work, our paper. And also we are using a hierarchical temporal aggregation. This is a very straightforward strategy we use to reduce the number of iterations we are using to predict a long period of weather. For example, if you want to predict the future 7 day, the weather in the 7 days later, if you are using a lead time of 6 hours, which is both NVIDIA and Google did, so the model of NVIDIA and Google can also predict the weather 6 hours later. So if you want to predict the weather 7 days later, you must iterate the model for 28 times. So it increases it causes the prediction error to accumulate very fast. And we are using 4 models with the lead times being 1 hour, 3 hours, 6 hours, and 24 hours, so that we can choose the proper model to use when we are predicting a time point in the long future. For example, 7 days later, we can call the 24-hour model only 7 times, so that you can see this causes about 20% decrease in the accumulated mean error. Okay, so this is a very, straightforward strategy. The cost is that you need to train 4 models, not only 1 model. So in the training time, you need to train 4 models, and in the testing time, there's no cost. There's no cost because and also if you are trying to predict a long time in the future, the prediction time will be decreased because you only need to run the model 7 times, and they need to run the model for 28 times, so the inference time is saved. Okay, so this is another trick. And regarding the computational cost, we can see that the training time is very long because you need to train the model on a large scale data set, and the data set contains like 60 terabytes of data, and each model has around 64 million parameters. So each photo is trained for 100 epochs in the whole data set, taking about 16 days on about 192 NVIDIA GPUs. So each model, we have 4 models like this. But after you train your model, the inference is fast because you can run each model, you can run each iteration with only 1.4 seconds on a single GPU. Even if you do not have GPU, you have something like your laptop. It also has a CPU like a Core i9 or i7 CPU. It takes about 1 minute. It's quite affordable, right? Okay, so if you want to perform the 7-day global forecasting, you only need to run in a GPU 7 times. It costs less than 10 seconds in total. But previously, with the conventional model, you need a supercomputer to run the conventional partial differential equation system. You need like thousands of CPU cores to run for several hours. So this is the difference. If you compute the time, the time, then we are about 1,000 times thousands of times faster than the conventional algorithm. But if you compute the power usage, then our model is more than tens of thousands of times faster than the conventional algorithm. So our trained models are released online, so everyone can download it and test it on the ERI5 dataset. Okay. So now we are reporting some results. For these results, I can use 1 sentence to summarize the results, that we are the first ever AI algorithm to surpass the operational IFS. This is the state-of-the-art accuracy at the time we release our paper. So the operational IFS is not one algorithm, but it is the algorithm the ECMWF are using every day to produce their result. So this is a changing concept, not a determined algorithm. But we are the first algorithm to work better than the conventional ones. So you can see that this is the Z500 is the let's say geopotential at 500 hectopascals. The T8550 is the temperature at 850 hectopascals. They are 2 upper air variables. You can see that the red line, the red plot is our algorithm. The blue one is the EC's operational IFS, and the black one is the ForecastNet, the best AI algorithm at the time we report our paper. So we are better than both, and we are the first one to surpass the numerical algorithm. We are better than it for about 10%. And also for 3 surface variables, the 2-meter temperature and the 2 wind speed components, we are better than it for about 10 to 20% in the RMSE or ACC. Okay, so and we can also predict the forecast time gain, which means that if you are given a tolerable error, then our algorithm can predict longer than the previous IFS algorithm. And also we report our algorithm in the northern hemisphere, in the southern hemisphere, and in the tropics. We can see that the forecasting skill in these different regions are steady. And specifically in the tropics, the advantage is much larger than the southern and the northern hemisphere. It is because the conventional algorithms are difficult to formulate some weather procedures in the tropics area. I cannot explain it very clearly because I am not learning meteorology, but the meteorologists, when they are seeing this figure, they told me that this is quite understandable because the tropics are very difficult to measure. Okay, and the forecasting skill in the different years, you mentioned, you remember that we have 3 testing years, 2018, 2020, and 2021. The forecasting skills through these years are steady. It shows that our skill is stable across different years, different time. And we have some visualization results. This is a Z 500 hectopascals and the temperature in 850 hectopascals. You can see that our result is here and the operational IFS is here. The difference lies in some boundary region. You can see that the AI algorithm tend to predict some smooth boundaries. It's much smoother than here, right? It is because that AI does not know physics. AI does not know anything about physics. It just try to fit the data. So AI, the property of AI is naturally tending to predict smoother values or boundaries. Also, we can see some similar things in the temperature and wind speed. Okay, and because AI is much faster than the conventional algorithms, it offers us a better opportunity to run ensemble forecast. Ensemble means that you run the algorithm multiple times in different initial values to predict either the mean value or the distribution of the future weather. So you can see that the skill is comparable to the previous AI. You can see that the forecasting error decreases when we are using more ensemble members. And more importantly, AI is much faster in running such things. If you imagine that a conventional algorithm itself, it needs to run about several hours in thousands of CPUs. If you want to run 50 or 100 members of ensemble forecast, it's a very large computation. But for AI, you only need 10 seconds in a single GPU to run one time. Even if you want to run 10, 100, or even 1,000 members, it's quite easy. It's quite affordable, right? Okay, so AI is much better or much more economic in ensemble forecasts. Okay, and also AI can do extreme weather forecast, but AI's skill in extreme weather forecasting is more or less weaker than the conventional algorithm because as I said, AI tends to smoothify the results, so it cannot predict the extreme points very well. The intensity of extreme weather events are often weaker than the conventional algorithms. Okay, but we show you a very interesting one that we are using the algorithm to track the tropical cyclones. If you are given an initial point of a tropical cyclone, we can use the predicted variable named the mean sea level pressure because we know that the tropical cyclones corresponds to a local minimum of the mean sea level pressure. So we can track the local minimum of this mean sea level pressure to track the path of the tropical cyclones. And we are using a very simple algorithm to process our predicted data. And then you can see that, for example, the initial point is here, and you can track the tropical cyclone all the way down here, right? You every time you predict 6 hours and you find the next local minimum of the tropical cyclone, and you use it as the initial point, and then find the next 6 hours, and so on. You can find the tropical cyclone's path. Okay, in the 2018, we found over 88 named tropical cyclones, and we are using our algorithm to predict their path. And we find that in the entire data set, as well as in the subsets of different regions and different intensities, our algorithm is always more accurate than the ECMWF high resolution system in predicting the position of the tropical cyclones. And we are showing two typical cases of the tropical cyclone, the Typhoon Conray and the U2. They are the two strongest tropical cyclones in the Western Pacific Ocean in 2018. So that we can see that the blue one is the prediction of the ECMWF's high resolution forecast, and the red one is ours. And the red one is very close to the true path, which is the black one, right? In the both case, it's like that. Much more accurate than the conventional algorithm. So it is because we can formulate the weather procedure in the tropics very well. If you remember, we showed that our algorithm is much more accurate in the tropics region than the conventional algorithm. So it also reflects in the prediction of the tropical cyclones. Okay, so after I show you these many results, I would like to summarize my talk. And in this talk, we show that an AI algorithm named Pangu-Weather shows great potentials in numerical weather prediction. It can beat the previous conventional NWP algorithm when you are using the reanalysis data as the input, and the experimental results show the strong results. And okay, so I think this is a good example of AI entering a new field that previously was not solved by AI. But we will not say that AI can replace the conventional NWP algorithm right now, because AI still have some, drawbacks. Because, for example, it tends to smoothify the results. It tends to predict weakened intensities in the extreme weather events. So this is this is the drawback of AI, and we want to continue developing AI algorithms. We want to improve them in the future. Okay, and in the future, I think AI for NWP has at least these three keywords: the more data, stronger models, and the better metrics. They are very important. And more data, stronger models, I think these two are very easy to be understood. But the better metrics, what does it mean? I will take a little time to explain this thing. Currently, we are using something like the RMSE, the mean square error, to measure the difference between the predicted weather and the true weather. But this is quite problematic. For example, you can see, let me draw an example here. For example, you are given an initial point of a tropical cyclone. Right? You want to predict where it goes in the future. For example, the truth is that 3 days later, it goes to this part. So this is the truth. And AI predicts that it goes here. It's a prediction. Okay, even now, the best AI system can predict this thing. For example, 3 days later, the best AI system can predict something like the mean distance error is like 100 to 200 kilometers. So this is the best algorithm we have now. even no matter for AI or for the conventional algorithm. So what does it mean? You know that for a tropical cyclone, the effective radius of the cyclone is often something like 100 kilometers. So the radius is similar or even smaller than 100 kilometers, right? It means that, so what does it mean? Let me explain this point. It's very interesting. So for an AI algorithm, if it predicts a cyclone exists here, right? Then when you compute the mean square error, the error accumulates for 2 times. The first time is that this true one is not predicted. And the second one is that you predict something here, right? There are 2 parts of errors accumulated. But if your AI algorithm is smart, is sufficiently smart, let me use this thing, smart, then it can predict that this tropical cyclone directly vanishes, right? If it vanishes, then the error will only be accumulated once, because this one is not predicted. But this here it will not have a new error. I don't know if I explained it clearly. So for AI, if it cannot predict the thing very, very accurately, then the best strategy for it is to predict the extreme weather events as it does not appear or it vanishes. So, but AI is not, AI is purely data driven. It does not have any knowledge about the physics. So it can easily learn, more or less learn this trick to diminish or to weaken this part. So that is why AI often tends to weaken the intensity of extreme weather events, because the weaker it predicts, the higher accuracy it will have. This is this is a drawback of AI, because it is bounded within the current evaluation metric. I think this is a very important problem right now, but I did not see any work or any research to trying to solve it very well. Okay, so I think the better metrics is very important in the future. Even I think this one is even more important than these 2 parts, because these 2 are quite predictable. If you have more data, if you can train stronger models with more GPUs, then your model will be stronger. But this one, currently, we do not have a very determined direction to go. Okay. Okay, this is my So this is my discussion that showing this example. Okay. And our work was accepted by Nature in 2023, in the past year. So the referees agreed with our contribution and the potential of our work. Okay, I will skip through this part. And our models were released online, so everyone can use it to try your own algorithm. And also the ECMWF has tried our model, and they have published a few technical reports to show that our model works on par with their numerical systems, and it can be very promising in the future. And also ECMWF has released Pangu-Weather as part of their operational suite in their website, and you can try that. You can search Pangu on ECMWF's website to see what our prediction is. Okay, so also we have a light version of Pangu-Weather, and we allow you to use about 1% of computational cost to run close accuracy with the operational IFS. Okay, this is our introduction of our work. So if you are interested in our work, you can scan this QR code for our paper and for code and models. And in the second one, you can also find the download link of these slides. So if you want, you can try. Okay, so this is the end of my talk. Thank you.
Thank you. Maybe we'll have some time for questions.
Thank you for the nice talk. So as you use the vision transformer for your model architecture, so you have to divide the whole global map into a number of patches and do some different level of message passing for each patch. And each patch is gathered to the reconstruct to the global map. So in this flow, so is there any discontinuity between patches with very close?
I see. We did not observe some discontinuity. I mean, we did not see some signs of such problem.
So even for the long period of forecast.
Yeah.
So you didn't observe that kind of problem.
Yeah. Maybe we are not so. We do not have sufficient expertise to notice, but we did not observe that.
Okay. Thank you.
Any questions?
Very good work. Thank you. I have two questions. First one is you use 3D models. I would like to know the cost benefit of doing that.
Oh, no, what?
I mean, adding the altitude, how much cost, and have you gained much from that? The first question. The second one is we heard from the news, Fengqing, Fenglei, etc. How would your work compare to the recent progress in that line?
Okay, thank you. So the first one is that we did in our early experimental results, we did have some comparison between 2D and 3D networks, and 2D and 3D is better. And in the later experiments, we did not report that on the paper because some settings are changed, and we do not have sufficient computational results to run both 2D and 3D, and we believe that 3D will be better than 2D. And I will say some in the early experiments, the accuracy or the error of the RMSE of 3D networks is about 10% lower than 2D networks. So this is a rough estimation. And for the second problem, I know that the models you mentioned, and but because they were not released, I cannot compare between. Okay, so the minimum, the minimum time, temporal resolution is 1 hour. But if you are mentioning the nowcasting task, for example, we are going to predict the future 10 minutes or 5 minutes. The ERF5 does not have such data. It does not allow us to do that. Temporarily, we do not have such data. Sorry. Okay.
So, any other questions?
So, will this model be used in the future Huawei device?
Yeah, according to the Chinese law, only CMA, the Chinese Meteorology Agency, can release weather forecasting to the society. If we do that, it is illegal. Okay, so for any software or mobile phone, also it can only fetch the forecasting data from some agencies who have such right to report the weather. Yeah.
Apply for.
You can try to. If you have the ERA5 data, you can try to forecast the weather, future weather, and you check it by yourself. But if you release it onto the public, it's not allowed. Yeah. But you can try. You can run our open source model by yourself.
Okay. Thank you.
Thanks for this talk. I just wonder, how would you consider the explainability of the model? Because, my opinion, the deep neural network, especially in this case, the large model, has very little explainability. So, do you think, well, the low explainability will affect the future, like the application? Maybe after all, the weather prediction is about decision making. So maybe the experts or the publics will want to know why the maybe 6 hours later it will be raining or something.
Okay.
That.
Very good question. So I think as the rapid development of deep learning, so the core part of deep learning is to build your system more likely on the data itself, not to relying on the human expertise. Also, you can see that currently the large language models like GPT is a black box. You do not know what happens inside, but it's quite powerful. So I would like to deliver 2 comments. The first thing is that the explainability is a big issue for AI, especially for the meteorologists. They will be quite worried about if the model is not explainable. They will not know when the model will report some very weird phenomena. For example, we tried sometimes when we are try to forecast the future path of a tropical cyclone, we can see that the tropical cyclone is split into 2. It's impossible, right? But because AI is purely relied on data, it can make some ridiculous prediction, but the physics models do not do this. So this is possible, and this is an issue. So the second comment I want to say is that in the future 3 to 5 years, we will see the combination of AI algorithms and conventional algorithms like a hybrid model. So AI can do something they are good at, and the conventional model will do something. For example, a very good example is also in the predicting the tropical cyclones. As I said, AI can underestimate the intensity of the tropical cyclones, right? But the path is very accurate. So currently, as I know, the meteorologists are tending to use AI to predict the path and using the conventional algorithm to predict the strength or the intensity and combine the results. It works very well. So in the future, we will see they combine with each other. Okay.
Thank you. Due to the time constraint, I think this may be the last question. If you have questions, you can discuss with Dr. Xie. Thank you, Dr. Xie, and all the questions from the audience.
Thank you.